In this video, we discuss learning outcome number 5 from lesson 5.2, which is all about using probabilities to determine if a number of successes is significantly high or significantly low. Now, we've already talked about this. We talked about this in lesson 5.1, but at that point, we hadn't learned about binomial probability distributions yet. So now that we know more about binomial probability distributions, we can use that knowledge to answer similar questions to those that we answered in lesson 5.1. Now remember, in 5.1, we said that X successes among N trials is significantly high. It's a significantly high number of successes if the probability of getting X successes or more successes than that is less than or equal to 0.05. Now, I know our probabilities are always numbers between 0 and 1 inclusive. They're always proportions or sometimes fractions, but it's helpful to translate those into percentages. So this is how I like to look at it and how I like to think about it. This is saying that X successes among N trials is a significantly high number of successes if the probability of having X successes or more successes is less than or equal to 5%. So if I translate that 0.05 into a percentage, it's 5%. So that means that that event is rare. It's very rare. It's very uncommon, and it's uncommon on the high end because it's significantly high when we're looking at X successes or more than X successes, and we're adding all those probabilities together, and we're saying that the probability of being in that, or if you're having that number of successes is less than or equal to 5%. Similarly, we say that X successes among N trials is significantly low. It's a significantly low number of successes if the probability of getting X successes or fewer successes than that is less than or equal to 0.05. Or alternatively, we can translate that to 5%. Now, this 0.05 marker is commonly used, but it's not absolutely rigid. Sometimes people will use the marker of 0.01 to talk about significantly high or significantly low values. That would correspond to a probability that's less than or equal to 1%. So that's very rare, even more rare than the 5%. And then sometimes people use 0.10, so 10%. But we're looking for probabilities that are extreme. Basically, if we were to look at these X values on a number line with our mean value there in the middle, these are going to be these significantly high values and significantly low values correspond to values on the high end of that number line or the low end of that number line. And we're talking about those numbers of successes, so that if you took that number of successes or more than that, or that number of successes or less than that, the probability in those tails is less than or equal to 5% or 0.05 as a proportion. Now we're going to return to this question. We've already looked at this question, but last time we looked at this question, we used the range rule of thumb to determine whether a particular value is significantly high or low. This time we want to use probabilities. And we can do that pretty easily now that we know about binomial probability distributions and all of the different ways that we can calculate probabilities for binomial probability distributions. So let's reread the problem statement. It says, standardized tests such as the SAT, ACT, and MCAT typically use multiple choice questions, each with 5 possible answers, A, B, C, D, and E, one of which is correct. Assume that you guess on the first 4 questions on this standardized test. This time we want to use probabilities to determine if 3 correct guesses out of 4 guesses is a significantly high number of correct guesses. So in order to do this, we're going to create a probability distribution for X successes in 4 trials because each guess corresponds to a trial. And we're going to define success to be getting that answer correct. That's a correct guess, and that's success. Now you can find these probabilities a number of different ways. You could use that probability formula. You could use intuition for X equals 0, 1, 2, 3, and 4. I don't recommend the intuitive approach or the formulaic approach here, because what you have to find is 5 different probabilities. So what I would recommend that you do is either use technology or look these up in a table. I think I'm going to use technology first to show you how to get this answer, and then I'll look it up in a table with you, and we'll see that technology and the table agree. So to do that, I'll bring up Excel again. I want to zoom way in. And this is the number of successes in 4 trials. So we'll have 0 correct guesses, 1 correct guess, 2, 3, or 4 correct guesses. And we want the probability of that many correct guesses over here. Now, these are binomial trials, because within each trial, you could have a guess being correct or incorrect. So you've got 2 possible options. We have a finite number of trials. We've got 4 trials right here. All of these have equal probabilities of success, excuse me. They have a probability of 1 in 5 or 0.2 as a probability of success. So this is a binomial distribution. So if I want to find the probabilities, I can use that binomial function again. So I'll type equals BINOM, and there it is. It just pops up for me. And then if you read the fine print, it says that that first entry should be X number of successes. So I'll highlight my X value over here. We've got 4 trials, so that's what we're asking, or they're asking for next. And then they want the probability of success in 1 trial. Remember, the options were A, B, C, D, and E, and only one of them was correct. So we have a 1 in 5 chance of getting correct, or correctly guessing, the correct answer. And we're not interested in a cumulative probability distribution. We just want the probability for X successes in 4 trials. So just type false for that last one, because we're not looking for cumulative probabilities. Hit enter, then take that corner, drag and drop, and this is what we get. 0.4096, and the same thing, and then this, and then this. I believe the ones in our table, the probabilities in our table, are rounded to 3 decimal places. So this is what I would expect to see in the table. Now remember, we had N trials, and we're looking at all the possible successes for N trials. So 0 successes all the way through 4 successes, which again corresponds to guessing incorrectly on all the problems. So you have 0 problems that were guessed correctly, all the way to guessing all 4 of the problems correctly. If that happens to you, then you're pretty lucky. So these are the values for the probabilities. Let's look it up in the table. This is the binomial table that will be provided to you during your exam if you're taking my course. So we've got the number of trials here. We've got N in this column, and then we've got the number of successes in N trials here. And we have N equals 4 trials. And so what we're really interested in is the probability for every single value of X for our probability distribution, for X equals 0, 1, 2, 3, and 4. And so we know we're going to look at one of these columns over here. Now to find it, we need to find the correct probability. The probability was 1 in 5. That's the same as 0.2. So I'm going to draw. I've never actually tried to do this. I wonder if it's going to let me draw. Oh, it is. Heck yeah. There it is, guys. I've got N trials and 0, 1, 2, 3, 4 possible successes. There's my probability P, and there is my probability distribution. 4 are 0.410, 0.410, 0.154, and 0.026, and 0.002. Let's close that for a second. I guess it's not letting me get out. You say clear. I'm done. Let me leave. Thank you. Okay. Let's go back to that Excel spreadsheet. We get exactly the same answer. So you can use technology or you can just look it up in a table. And either way, you're going to get the same answer as long as you're using your technology correctly. No, I don't need to save that. Okay. All right, so we're here. And this is what we found using technology and looking them up in a table if we had used the formulas for probabilities. So we would have looked at combinations and then multiplied by the probability of success raised to the x power, multiplied by the probability of failure, raised to the n minus x power, where n minus x is the number of failures. If you would have worked all that out, you would have gotten these probabilities as well. Now we're trying to determine whether 3 correct guesses in 4 trials is significantly high. So if we want to do that, we need to look at the probability of getting X correct guesses or guessing correctly on X problems, or something more extreme than that on the high end, because they're asking if it's significantly high. So I'm looking for X equals 3 correct guesses or X equals 4 correct guesses. And when I'm saying X equals 3 or 4, whenever we hear that word or, we've got to use the addition rule. You just take the probability that we have 3 out of 4 correct, and then you add the probability that we had 4 out of 4 correct. And we get 0.028. Now, if I'm trying to determine significance, we use that 0.05 cutoff in this class. So I'm comparing this probability of 0.028 to 0.05, and that probability is less than this probability, and therefore 3 correct guesses out of 4 is significant. Now, if you want to interpret it using percentages, and I prefer to, this is what this says. It says the probability of getting X or 3 guesses correct or 4 guesses correct is only 2.8%. The probability of being in that category with 3 correct guesses or 4 correct guesses is only 2.8%, and that's very rare. It's even more rare than a 5% percentile cutoff. So that's what we're looking at here. We're comparing this 2.8% to 5%, and we're saying, since that probability is less than or equal to 5%, we're going to say that 3 correct guesses and 4 guesses is a significantly high number of correct guesses to get by chance. Now, of course, we should use probabilities, those proportions between 0 and 1 instead, but the percentages really help me to interpret these numbers. I hope they help you too.